we're transmitting again. Let's see. So we're going to try some computational conversations today with talking about malaria, maybe. Were you able to see the structure of the data set? I did leave the following file on the path. I think this one should work for your computer. It's malaria.wdx, which supposedly it works in any platform. And well, so it has an association in here. And of those, basically what I have here is on results. There are different pieces of data, and also I have code. So the results data set, basically what I did is I went to the World Health Organization and downloaded the different data sets that they had. Some for the different countries, estimated cases, reported cases, deaths, and whatnot. And I put it under one data set that you could pull information from. For example, if we want, just to make it easier, I'm gonna create a data set with this. So we can call it. So there are different characteristics that I pulled in. If we do a union of the characteristic, you can see that we pull the confirmed cases, which is the cases that are reported, estimated cases. You may not get all the cases reported, so they mix through a certain methodology estimated number of cases, and they have a lower and upper bound, and then the reported deaths. So with that data, which is all here, we got different countries which reported let me clean that up. Those are the countries that reported that data, and also we have different regions in which those countries are grouped. Which is in Africa, Asia, North America, Oceania, and South America. What else did I do? So we were looking at results. And so that's a data set. We discussed the data set. I did create, now we have him here, but what I did create some data around the geography, so they're easy to pull out. And you can use this then with the code. So you got countries, regions, administrative divisions, and a rule set that it's easier if I want to all the list of all the countries that are within that region of Asia that have the data, you can pull it from there. The other thing I did with that, so that's geography, it's in time series. So if we look at the time series, basically what I did is I pre-processed all the information. So we have a, oh, that's not a good idea, let's do this. So we have different time series from the population of those countries. So this information I pulled from some UN file because I got a time series, let's say we want the historical trend of the population in Argentina. So we got the data from 1950 onwards. So population holds that, and then we could say, okay, show me the confirmed cases of malaria in Argentina. Those are the number of confirmed cases since 2000 and to 2007, and then based on those things, using the population that we pulled from the UN, then we could do the confirmed cases per 100,000, so you can compare across different countries. So numbers are less than one case per 100,000, which is much better than if you look at other places like, let's say, Democratic Republic of Congo, which are in almost 20,000 cases and growing since. And then we can look at this, which is when the civil war started. That's not fast, okay. So there was a civil war, 1997 to 2000. And 1997 to 2003 civil war. There's continuous conflict since 2003. That could be one of the explanations. So that's that, for example. And then what else? I did that some code. Which if we activate, let's see what happens. Let me do reported deaths. It does take some time the first time to load it. I think it's looking for the data and the polygons and whatnot. Back in Wolfram. Let's wait a little bit.
So meanwhile, what we could compare is I've got data from the WHO. So I sent this.
If you want, we can also try you sharing the screen, right? Because it will be transmitted, I think, as it's capturing on my side.
But for now, I just send you that.
Okay.
In the chat.
Should get it. That's awful. Oh, dynamic updating is disabled? No, it's enabled. Okay. Let's try this. That's odd. Let me try this. Maybe they didn't like the inactivate thing much.
Yeah, looks like it.
Okay, we're gonna have to try something else. Let's see with this. Malaria world. Okay, so what do we see here?
So this is the incident rate.
Yes.
Per region.
Mm-hmm.
And let me just check. So this is per 1,000 of population.
Per 1,000?
Yes.
Okay, so this will be Africa, right? Which is the big line. Oh,
yes,
okay.
that's Africa. So you've got a table for this. Oops.
So this is the table you're sharing. Let me see. Copy here. per 1,000 population at risk. It's pretty sad. There is not real improvement in Africa. Actually, the Americas are up. Let me see if we can get this code to work. Because
I think it's that this is of course quite large scale. So if you go to websites like the Oxford one, there's an Oxford map. You get much higher resolutions. Let me check. So I sent 2 links.
Okay. I'm on the link. Oh, the map. Oh, yes. This is a very good tool. So from here you can look at and explore the map, right?
Yes, the problem is I could only export the data at the moment. So it seems that there should be in the box that you see with the red bits, there should be something to download, but I suppose you have to be registered or so. So the African countries are more interesting. You see more color.
Yes. So here it's what we're looking at is the rate of.
And you can now click on the right hand side. There is a circle with 3 white lines there, and if you click on that, we should be able to go down to the 3rd from the bottom, and you can export that as an image.
Yes. Let's see. So there, yeah, the Plasmodium falciparum is one of the 3 or 4 different parasites.
Yes.
That cause the disease. So that's probably taken. This would tell us if it's taken from the blood, right? They do some sampling of the blood, and that's how they get the statistics. So export as image. There's the image, which I think we want to process this with Mathematica and see if we can yeah, because the data points cannot be obtained, so well, maybe that would take us a little bit of time, but we could use this as to translate the data, the colors into.
It seems that you can export that as a GeoTIFF in principle, and then it's easier to get to the data.
Yes, so but then you would need to be registered, right?
I suppose, yes.
Yeah. Let's see what happened here. Oh, look, finally it worked. I brought the data, I brought the code from the file. So basically, what I did is like we were looking at your table here, right? So
yes.
You got the Americas, right? So
yeah.
The Americas have been going up, so we could do, and we were looking at incidents, right? So let's assume that this is confirmed cases, and we're gonna do it for South America. It will come sooner rather than later. that takes time, eh?
Yeah.
Let's see. That's all. I was running it today and it went quite fast. Downloading values. So it's bringing the polygons. There you go. So these are the confirmed cases. And if you can see, it's being driven by the crisis in Venezuela. Because if we look at the other the other geographies, and let's do per 100,000 confirmed rates per 100,000. You see, it was slow because basically it was bringing the map in. Venezuela went from, they were around like 180 cases per 100,000, and since 2015 it just skyrocketed with the whole economic crisis. Guyana goes into a strange frequency pattern. Colombia down, Ecuador, great job, Peru, and Brazil, and the rest are getting controlled. So that's an interesting aspect of why the incidents are going up. It's basically driven by the crisis in Venezuela. Oh, this is interesting. Eastern Mediterranean, so Syria? That would be in Asia. One of the things I was looking at, but I couldn't find data points, is that if you look at the literature, the way to reduce the incidence is it's basically drainage and attacking the vector, right, which is the mosquito. For those two things, you need an infrastructure, and the poverty. Usually, the poverty levels that you see here, or you have conflict, makes the infrastructure work quite difficult. And the other thing is, if you don't have that, it's on droughts. You have something called the Palmer Index, and but I couldn't get any data points on that to analyze like those frequency patterns that we saw in some countries that might be explained when you have a drought. There's less water, stagnant water, which diminishes the amount of mosquitoes available to be attacked.
Yes.
That's quite odd that it takes so long. Because that pattern that you see there, it's odd.
Yeah, it appears that there is a very strong fine structure to the distribution of cases. Let me just see where I find the chat window again.
Okay. Oh, there you got that nice mosquito.
Let me just try.
Were you able to find any information on the models that they run?
Yes, there are quite. Again, I'll send you So there is a project funded by the Melinda and Bill Gates Foundation, I think, where they study also the height differences. So if you go up the mountains, because it gets colder, the
Yes.
mosquitoes don't go there, and that can give partial protection.
This came back, and
So I sent you 2 paper in the chat. 2 papers should be open access.
oh, very good.
So relatively, I mean, there is it's table 4, I think, in the first paper. There is a whole range of
Table 4.
models.
Oh, table 4, yeah. The Ross model.
Yes.
So yeah, that was the guy who first figured out what was going on with the transmission. Were you able to play with the model at all?
No, I haven't implemented it, but it shouldn't be too difficult.
Yes.
I'll try. So there are the ODE models, for example, table 4, model B, or A. So the A should actually be relatively easy to do.
Yeah, that's straightforward. So basically, the number of infections by time is based on the biting rate, how many times a person gets bitten, and a proportion of how many of those bites will transmit the disease times M is. This is very similar to the standard epidemiological model, right?
Yeah, it's just it's SEIR, this one.
Yeah.
It's similar, yes.
Yeah.
So let me see.
Yeah, it's in the. What was the name? Is it Lochte? What was the name of There was a standard model. I can't remember the name. Lochte. Can't remember the names, but it's that set of equations. SIS. Susceptible, infective, and deaths coming apart. Yeah. So one was the susceptible, and the other one is the infective. which is similar to what we were looking about here. So IH must be healthy, and the yeah. So I thought the confirmed cases were driven by. So this is not using. So this is oh, this is because it's including everybody. But this is confirmed. I think the big part is here in Yemen. And here, let's see. Wow. And there's no data on Syria.
I'm just trying to what I'm doing here. So A, say 1, B, you should look that up in the manuscript, but okay. So what's that? So my H, mu, LDN. Oh, here we go. So let's do this. I sent you a model. Parameters are just all 1 at the moment, but there we go. And that is still an error, but probably fixable.
Okay. Very good.
Quiet, I love it.
Yeah, shut up, right?
Exactly.
So IH, IM both fall with time. So let's look at the equations. That means that based on the parameters that we're seeing, it's not enough to reproduce and grow in the population. It just dies out.
Okay, so let's make this C larger.
You can show with a manipulate, right? How that would work.
Yep. Yep.
Okay, let's show that. That would be interesting, maybe.
Oh, I just check.
Let's try this with basically what we're saying is with the solutions given by this equation, this set of ODEs, let's plot them.
Okay, so it says something about the value. So
yeah, so we're gonna do a
okay, so that should be mean biting rate is very small, so the A should be 0.02, say,
from
or 0.1, we can make it, and B 0.3.
we're gonna call this bite rate.
Yeah, the mean biting rate is 0.01 to 0.5 per day.
Perfect.
So let's do that 0.1. The B proportion of bites that produce infection in humans is between 0.2 and 0.5, so let's make that 0.3.
Proportion bites, okay.
I'm not quite sure where they get the M.
So here we're gonna say infectious proportion.
Yes, I don't know what our reproductive number is. Let's check that. N A squared BC times mu. Switch that. Okay, so I see another thing.
Okay.
In the paper, they say that MA squared BC divided by R mu 2 is R0, and R0 is the average number of successful offspring that a parasite is capable of producing. Malaria can spread in a population only if R0 is larger than 1 epidemic. When it's maintained in a population without the need for external inputs, R equal 1 endemic. Disease-free population is possible when R0 is smaller than 1. So we would like to make R0 larger than 1, and at the moment our R0, if you evaluate that function,
it's 1.
Is 0.075.
R0.
So if what I just sent you contains parameters that I chose now in the model, I modified that according to the paper. So these are the parameters that are used.
Okay, do you want me to put these parameters in? Okay.
And we want this to become a little bit larger. So the A and the B are given. What we could do is we could make probably the M larger and the R smaller. Okay, so what happens?
What did I do wrong here? Okay.
So if I choose the parameters as I send you now, we get an R0 from 1.5, larger than 1, epidemic.
Okay, so let's do that. I'm going to copy the equation again.
But it doesn't do it. Well, perhaps it does, actually.
Rid of the manipulate. So I hate this bracket story. Okay. I'm missing a bracket here. No.
So for me, if I run this,
So
I now get this here.
send me the whole model again so I can paste it correctly instead of trying to debug the where did I leave my I just wanted to see which one was what. Does this need to add up to 1? No.
Pardon?
So
R also needs to be much smaller. Oh, now this looks much better.
that looks so this would be on an endemic.
Yes, and we've got a rather large. So the R0 is 20 in this case.
Mm-hmm. Very nice thing to play around with.
Mm-hmm. How do we get rid of the error message? The ND source to
On this? Yeah, we
this
can
is
do this.
video for the system. Some components are different from those specified. Well, So actually we should be able to just program the manipulator in a second. B is 0.3 and goes from 0.2 to 0.5. So that's B. C is 0.5. C 0.5. But let's say actually that goes from 0.1 to 0.8. M, ratio of number female mosquitoes to that of humans. And we have N equal to 40, but it could go from 0.5 to 40. And then R is at the moment 0.03, but R could go from 0.005 to 0.05. So that's my R. And then I've got the mu2, which in our case is just a mu. See whether that makes sense. U2, mortality, and that is 0.1. It could go from 0.05 to 0.5. Oops. Oh dear. Okay. I send you something.
Okay. Very good.
So I think I've done that basically.
Yes, you did.
No, there's something missing. You only have the from acquired. There's a manipulator at the beginning that you haven't copied.
Yeah. I need to clean this up. This. Oh, yes. There we go. So that's a lot of parameters right there. That's very cool.
Okay, we should label this because this is difficult too.
Yeah, we don't know what everything is. So yeah, we do need to label this.
I can do this, I hope.
So this would be, this is the Ross model, right?
A is mean writing rate.
And then we can do.
Okay, that seems to work. B is proportion of bytes that produce infection. Bit long, but okay. C is proportion of bytes by which mosquito becomes infected. The M, ratio of females. R Okay. And then we do have to label that. And that comes out as IH. The infected humans and the infected mosquitoes.
Okay. So IH is infected humans and IM infected mosquitoes. Okay.
Okay. I think I've got that. So
You sending it back?
if I find my chat window, I post it again.
All right.
And send.
Very good. So basically, this is the ROS model, right?
Mm-hmm. And if you compare that to figure 3 of the paper,
Figure 3 of the paper. Let's go back.
it doesn't look too bad. They integrate a bit longer. They integrate to 250. But we can do that.
The paper again. I closed the paper, so I'm opening it again, so we can share that in the screen.
They start at lower values. Let's try that too. So, oh yes.
What page?
So I'm trying to do that. If I could.
250.
I send you the link to the paper again.
Yeah, I have it. I have it. I went back in the chat.
Yes.
You can always save the chat in case we need to recover it.
Mm-hmm.
So from 0 to 50, prevalence. On the wrong screen.
Oh dear. That's also no idea what I'm doing here. So, yeah, that's bad.
Yeah, not very stable. Per capita rate of mosquito mortality. Yeah.
It's also getting weird if you make the starting human population exactly 0 in the infected rate. So this here looks, I'm sending in the chat now, looks pretty much like in the paper.
Let's copy that. Yeah, it does. It looks. Let's put one against the other. There we go. Yep. Looks the same. Look at that.
it's not quite the same, but
Not
we might
quite
have
the
seen
same, yeah.
the parameters used in this image are also different from the ones that we used. There the A is 0.2, for example, in the paper, and we don't have it at 0.2.
Now we do. And B is 0.5.
0.5.
C is 0.5. M is 20. .01. And what is the last? MU.
It's mu2, so 0.12.
0.12.
Yeah. Now yeah. Well, it's not too bad. This looks quite okay.
Yes, it does. Although, okay, so that's that. Perfect.
I think that's because we don't start at the very same initial conditions.
Yes. Exactly.
But we don't know what the initial conditions are for them. And I guess you need to make the infected humans smaller, which is also the case for us.
Infected humans.
So if you make the infected humans smaller by a factor of 10, the initial condition for IH.
So now you got 0.1. You want it even smaller?
I think yes. I think one small, because then it takes longer for them to come up.
Yes. Correct.
Now if you make it even smaller than that, then we're getting there. The problem is if you put it to 0, you get an interesting error message.
Let's see. Yes.
Well, not error message, but yeah. But that's numerically, I think that's just numerics. So if we increase the precision or something, that should go away. Yeah, it goes away. If you want to be able to put it to 0 and you put a working precision of 30, then that goes away.
Okay. $20?
30, let's be generous.
Okay. So now we do 0.
IH, yes.
There you go. Absolutely. That worked out.
Mm-hmm. Yes. And that's time and days, so we can look at this.
Let me take this call. I'll be right back.
Okay.
Hey, Nassim. Yes, I'm Sorry about that. That was an interesting live stream. The guy who is in charge of the screen goes away.
Yeah. Well, so I've got two more options for the plot.
Let's look at
that
that.
I will send now.
That looks better. Yeah. Ratio. So that's a lot of mosquitoes right there. Oh, what's the number here?
40 probably, yes.
So we kill mosquitoes. It makes no. It just delays the situation, but we get to the same level of infected humans, which is point something. 0.2. So killing mosquitoes.
It's probably only going to be there.
Average recovery rate of humans. Per capita rate of mosquito mortality. So we kill them, or what's the story with this? This sucks. Okay.
Yes, if you try to...
What I was trying to figure out is there anything that you can do to lower the...
yes, if the ratio of female mosquitoes to humans gets lower than 1, at the very beginning, so you can do this. You can go to...
Oh, that sucks. That sucks big time. So basically, yeah.
It's a bit slow on your end. This is... If you type in the box just 0.65.
0.65. Okay. Basically, you kill them all.
That could be, for example, if I move up a mountain and they can't, in that climate,
yes,
reproduce that well.
So let's leave it at 1.
Actually, it turns out if the ratio of female mosquitoes to humans is 2, it also still seems to be going down then.
Did I kill this thing? It's really slow.
It's probably because you're streaming, because this is really fast when I do it.
Yeah. So you said 2?
Mm-hmm. Yeah, I think it should still decline.
Yeah. before. It's amazing, eh? You don't need that many mosquitoes.
Yeah.
They reproduce much faster than we can, so.
Now it would be nice to copy these and put them on a grate somehow and make the parameters depend on the grade, on, say, the ratio of female mosquitoes to humans depend on the temperature. And the temperature is not the same for every point on the grid because there are mountains or so.
Yes. So say again.
So basically, so first step would be to have an independent, but make a grid. Just a grid, and let's say the birth rate, growth rate of the mosquitoes depends on where on the grid you are. So you have a grid with patches where it's warmer and where it's colder.
Mm-hmm.
And where it's colder, the ratio of female mosquitoes to humans is different from other areas.
Yes.
And then I would hope to get images which are similar to.
So that's something that we could try. Let's say, what is the median temperature of mean temperature in
Can you try to decompress that? I'm not sure whether that works.
let's give it a
Send
try.
an image.
Yeah, so I'll
Just the entire kind of thing, just decompress. Let's see whether that works. I'm not sure. Yeah.
no.
Ah. Okay, so how do we do this then? Need to do it. So
iconize it.
Yep.
They don't have any. Let's look at Angola. Okay.
Because there's a great fine structure depending on probably temperatures and things.
This is Haiti, right?
deaths per 1,000 per year.
That's low. There, yeah, it's 80 and
Geo-elevation for that probably.
Relief map.
Oh gosh, explain that.
Yeah, explain that. Right? This red is supposed to have more incidence?
One is what are the two different?
I can't read it very well from...
Yeah. So on the left it's global mapping, and on the right it's country level elimination mapping. Population below threshold. Cases per incident rate.
So, blue is higher or lower? Higher.
Blue is fewer incidents, red is high incident numbers.
I would have expected the temperature to be... I mean, this is the mountainous area, right?
Yeah.
So there are other parameters that we're not taking into consideration. That's damn slow.
But it's you, so it's fast here.
Yeah. You want to take control of the screen and you share the screen?
I suppose it's the streaming business.
Yeah, but if I stop sharing and you share your screen, right? Then the evaluation will happen at your end, and all I need to do is transmit. So if you want to go ahead and share your screen.
I'm not quite sure what I'm actually sharing at the moment.
I don't see anything.
Cool.
All I see is you and me. So let me see. Okay.
Can you see that now?
Yes, I can.
Wait. It doesn't. Here the rate perhaps. I don't know. Mm. So basically, okay, let's try that. So if we have that, okay, so let's do quantity magnitude, and let's show just first couple of them. Okay, right. Not enough. How many do we have? Good. So what's the dimension of this? Okay, that's not much. Right. Okay, so let's try to find what the so these are the this is height in feet, I think. Right?
Yeah.
Okay, so the first thing we want to do is we want to x smaller 0 0.
Perfect.
See where that is worked. No, we're done.
Underscore. Yeah.
Yep, that's better. Yeah. Okay, so basically everything that's now sea level should be gone.
Mm-hmm.
Should make a difference. Okay.
Perfect.
So now we have a matrix. Let's plot this. Don't need to do this. Okay.
Good.
So that's now the.
It's reversed.
Well, it's white for ground, and
Yeah.
I want to.
No, but the island is it's the other way. You need to reverse the reverse.
Because, well, the higher values will mean lower reproduction rates.
No. What I mean is, it's the mirror image of the.
Yes. Thought I had done this here, but no.
I think it's a matrix plot that it's putting it on. Yeah. Now we're talking. Yes.
Do I actually need them?
That looks good.
Well, there we go.
Yeah.
Okay. So, what do we want to do? We want to. Okay, so that's kind of the. What do we call this? Let's assume that the temperature goes with somehow with the height. So this is basically the ground matrix.
Yes.
That's, I don't know, no better idea at the moment. Okay.
Perfect.
So now, if we have our solve function, and this will be really slow what I'm doing now, so we take this,
Yes.
Oh God, I should have killed this one anyway here. We now need all our parameters as we wanted them in principle, so we say A, we want it to be 0.1, is this correct? Not quite, is it? C 0.5, is that we wanted? C 0.5 is correct. M 40, okay, so more or less this should not work. It's less than fine. What's going on? Why do we have a problem now? Oh, because I used quiet there, did I? Okay, so, and now if we ask, so basically this kind of thing saturates after 50 steps. So if I go to 100, but that doesn't matter, it's quite quick. So if I ask what these values are, is there, and then ask, I want this, and I want the time to be 250, then it doesn't work because interpolating function. Okay, let me see. That's fine. Will work. No, it doesn't. So I put them here, and then oops. Yes.
Yes.
So these would be for this particular situation. Would be the stable rates at the end, the percentages of infections in the human and the mosquito population.
Yes.
Okay, right. So, if I run this, that's what comes out. Brilliant.
Perfect.
So, okay, right. So, if I now take my ground matrix dimensions, and let's see. So if I want to get the...
So we need a function to...
Yes, and the function should be the ratio of female mosquitoes to humans, so that's the M. So I want the M to change.
Okay, so what equation are you going to use for... what was the maximum height? The max of the ground matrix?
Exactly, so the max of the... So if I take the ground matrix... Okay, so if it's 0...
Do we have an equation on temperature based on height? And, starting from T0...
Yeah, let's do it just linear, I would say, just to have something.
Yeah.
It's not correct, but...
yeah.
Also, we want, what happens if I put the
So-
m to 0? What happens then? How does this look? Okay, that's 0. That's nice, because that means we have no, at ground, at water level.
No, the thing is that
Yes.
so you have high temperatures at the bottom, okay? And as you go high, the temperature will be lower and the rate of mosquitoes will go down. So
Yes, but if this is 0, if this is a real 0, it's water, and in water there should be no infection.
no, in 0 the temperature is higher.
Yes.
Right? So
and
you have a
this
higher
number
rate.
here, this
So-
is the max. So it goes from 0 to that. At ground level, it should be high, so it should be about 40.
Yes.
And at this level, it should be, say, 0.
Yes.
Just to see. So what we want a function that goes
From 40 minus 40.
Ground level is 40 minus. Now we take
40 divided
by
by
height,
yeah,
divided by
that number
this,
times 40.
Well, that's quite precise here.
And times 40. No, times 40, yeah. So it will be 40H.
Yes.
Yep. 240, 88, 500. Yep. Perfect. So that's it would be m.
No, that's I don't like that, because my problem now is that I know that this goes to 0. It becomes small when this number is about 2.
Okay.
So that means only the greatest heights play a role here.
So then you can do.
And so to fix this, I just do this. Oops, no. I just do. What do I do?
Well, we can kill it at 70.
Oh, this is good.
You like that? Yeah.
And that's too much. That's probably, let's take this here. Why not?
Yeah, why not?
Okay, so now we take this thing and the m is going to be an h, is going to be dummy. And what we do is we put the dummy equal this there. Agreed? Put this in front. So now we have a dummy. So what happens if we run this and set the age to, say, 1000? We get some weird values. Okay, and if we set this to relatively high values like 6000, we're at 0. That's fine.
Perfect.
So that's h.
Yes.
Okay. So, oops, what do we do now?
So you can create a.
Okay, so now I do a table.
You can do a yeah.
And do the I from, what was this? Ground matrix. And I'm definitely confusing now the order. So the I goes from 0 to 1 to 440,
Yep.
and the J goes from 1 to 573.
Mm-hmm.
That's my table. And then the H is the ground matrix of ij.
Perfect.
Do we think that could be correct?
That looks good, and you're gonna have 2 values per cell.
Yes.
So that would be the incidence rate table.
Okay. Do we want this like that?
You want to do 2 separate ones, one for the mosquitoes and the other one for the human? Or you want to have it as one?
It should be easy to, if we have everything in a matrix with the 2 numbers, it should be easy still to plot. It's, I think.
Run it.
If it comes in what it shouldn't be, because then otherwise you might have to now do it twice. So
Yeah, let's do
let's do steady states and monitor something like this.
Yep.
And we should see when it's over.
Yep.
Oh God. Yeah, that's not going to work, is it? So, okay. First of all,
instead of 250, do it.
This curve goes, it's at 50, it's fine.
50 is fine. And do
Still
50.
Don't like that.
No, 50 at the ND solved level.
Yes, as well. Yes, sorry. Not much of a difference, is it?
Not much, no.
That takes, anyway, that's much too slow. So what do we do?
Working precision?
Working precision. No. Then we can't check.
We can't compile, no? This won't compile.
Okay. Wait. Well, this doesn't make a difference. Is that slow? Are we doing, what can we do faster here? So I wouldn't really have to do the substitution every single time.
Yeah, you can take that out of the thing and put a value on each one of them, right?
Pardon?
So set those as variable outside, right?
Mm-hmm.
And outside the definition, and then just go for it.
Wait. Am I just, wait, what if we do this? This is, wait, if we do this there and say parametric in dsolve, then take this thing as a parameter. Shouldn't that work? Because now I should just, so if I evaluate this and say something like this there, if I now give it an n, how does that look? Oh no, how do I do this?
You need to give the m first, right?
Pardon?
You have to give it the m value.
Yeah.
You're missing the m.
Okay. And now the t.
Mm-hmm.
And no. That shouldn't. Too many parameters in.
Maybe need to put in.
Oh god. What is that like parameter can be solved? Parameters. So that's 10. Okay.
So okay.
But then I give first the parameter. I set the parameter to 1. Evaluate this. This should be the parameter.
Uh-huh.
Huh. Does that look about right? Oops. No, that doesn't work. That's interesting. Okay, so I can only do that with 1. Oops. Okay, so that's all I can do. Do that then. What's happening now? This seemed to work a moment ago.
Yeah.
What's going on?
Okay, IM. No, you need to put the IM and then the T. You're missing the T in front there. Yeah. Okay. So.
Okay, that's just my typical mistake that I'm happy to live with.
Looks good.
Cool. Right, so this is the guy I want to change now.
Yes.
This is going to be
The ground.
that there.
Yeah.
And that's also bad, isn't it? I should do this. I shouldn't do this with. This is a matrix. I should just calculate this matrix directly for all of these parameters. And then use functional programming, I guess.
Yes. Mm-hmm.
But because I'm not sure how to do this, okay. And table. This I can actually do all of this. And at the end, I can do all of this. And I should be able to. No. better.
Much better. All right.
Mhm. Oh, come on.
No, you got 2 fields per. So
Yes. Let me see whether I just look at the first couple of them just to see how this looks.
yeah.
Not very good, does it?
So what happened here?
Why doesn't it know
Maybe evaluate.
my ground matrix is gone? Oh, probably it just died in the middle of it. So or I had to abort or something.
Yes.
So that means that's oh dear. Still not really.
No, because you must have lost the parametric functions
Yeah.
too. So you need to solve that. Yeah. And now we'll go.
Not so nice.
Not that faster.
No. It'll take too long. That's to 400. Then we're sitting here for half an hour.
Maybe what we should do is we can do it in the area of interest, right? So if you do the matrix plot again, and we know that it's between, let's say, 30 and 40 in one rows and 50 and 60 columns, right? We just zoom in into that area and look at that instead of doing for the whole universe.
Yes. I still wonder why is this so slow?
I think it's all the messaging that it's coming out. There should be no other reason by that except that. Do you want to do the working precision again? High and see what happens?
No.
Nope. Okay.
Problem is it is still they still make the error messages, yes. Giving initial conditions for all dependent variable and their derivatives. This is weird, haven't I done that? So this is the first one, that's the second one, and I've got 2 initial conditions, and for the derivatives I don't need initial conditions. Why is it complaining?
You want initial conditions for the derivatives too.
Why? It's a first order.
Well,
It's 2 of first order. The initial conditions are complete. Ah.
So that was it?
Probably not. Let me see. If this is it, then... Okay, let me just check. So if we take this table and we make it really small... Oh, it works.
Very good.
So this quiet should then
go away. Now we're talking.
clean this up. Yeah, internal error messages, that makes things slow.
Excellent.
So now we have to run it again and do an if condition, because this is going to be rubbish now.
Rubbish?
Yep, because on the C, I think where the ground matrix is 0, we get 40. And that means we have lots and lots of infections over the oceans, over the sea, and that doesn't, I don't think we want that.
Let's see what happens. So do you want to make
this is 2 always, okay, that's fine. So all 1, 3, so all 2. Yeah, that's pretty much the same. Makes sense, I think. And what we do here is...
What you can do is...
What did this do?
If it's...
Well, it looks like this, but what we really want, if this is 0, we want this to be 0.
So the ground matrix...
So if ground matrix xy is 0, then 0, otherwise that there.
Yeah.
Ugh, that will be slow.
So why don't you go back to the other thing and make this thing the Everest on the ground matrix? Everything that's sea level, make it 8,000.
Everything that's on the sea level, I make...
No.
So now everything that's on the sea level...
No, what you can do is just don't do the if. Get rid of the if condition.
Yeah.
So basically on the ground matrix, we just do a replacement of 0 for 8,500, right? And then it will be like a wall, and then the formula will just immediately put it to 0.
So what we do is...
Let me see if I can send you that.
This is the dummy thing. And in this dummy, everything that's exactly 40, we set to...
I sent you something on the chat.
No.
I sent you something on the chat.
Okay, having a look. Check there. Okay. Yeah, but that's this is... Okay, I think, okay.
So then you can simplify.
That means we go to... I do this first. Why is my ground matrix now?
I think it's just a copy thing.
Okay. No, that's because you divide, yes. Okay, but this is now, my ground matrix is wrong. So we do the ground matrix again.
No, you can go back to the top.
Why is it this? Oh, because I do weird things. Yeah, I don't want that.
Yeah, you don't want that.
Still slow. What's happened? Looks good.
Looks good. Let's go to the ground matrix definition at the top. Instead of if it's less than 0, put a 8,500 there. Right?
If x
is less than 0, make it
0. Oh, smaller equals 0.
Yeah, 8500.
Okay. Put this there.
Yeah. Less than 0, right?
Yep. Shall we try it?
Yeah.
Like this. Then we don't need this.
You don't need that.
We don't need that. We don't want this. And here. But it's still. Why is this now slower than before?
Are we getting an error message again? You got a quiet.
Oh, I know. My bad.
Yep. You may want to delete the other statement so we don't do the same mistake again, right?
Yeah, so the red means lots. This is low line, so it's warm, so we've got lots of mosquitoes.
Yes.
Here it's the second one is the
Humans.
mosquitoes. Actually, the mosquitoes are
the one on the top.
Are they? Because first is humans, second is mosquito. This is the first, and that's the second. That's humans, I think, and that's mosquitoes, isn't it?
You're correct. Yes. No, let's see. Okay. It says monitor.
Okay, so this is also because
No, the
it
first.
looks now it's just at really ground level. This is good. So we're too conservative with this here. So this falls too quick. So let's do this. Let's do that. And what did we say? 0.2. So if we go here to 0.2, I would now expect that there is more red. Hopefully.
So the first one is the mosquitoes, right? Because if you see, it says IMT and then IH. So one is mosquitoes, two is
IH and I mosquitoes.
The first one is mosquitoes.
Oops.
That would be humans.
But this is 2. And 2 is mosquito.
No, but look below on the monitor. You're putting on the steady state. The first one you're putting is the mosquito, and the second one you're putting is...
I do this. Oh dear.
Yeah.
I shouldn't do this. Yes. Well, there we go. Okay. So, humans. And plot label most. Oops. Okay.
So,
and now, because I can't compare them, I would like to do this on the same...
What do you want to compare?
Well, I would... because this rescales to the complete color set. And this is why, because this ratio, this is basically a ratio thing here. So I think what we really want is, if this is between 1 and 100, we want the color scale here also to go from 1 to 100, really.
So you can actually build an image data, right? And make it black and white, so...
This color scale, color function scaling, false. Is that what we expect? The mosquito population is much higher.
Mm-hmm.
The human population is smaller.
Do you want to do it in a monochrome or gray levels?
Why?
I don't know. I can't see. So white would be in the middle, right, on a temperature map.
Color, legended. No. What was that?
Let me see.
So what did I do here? Temperature map. Zero to one.
Just without the 0 to 1.
Yeah. Oh, quite idea.
Interesting.
Oh, that's good.
Just do a row instead of graphics row.
Yeah.
That's better. That's so. Show me the map that you originally shared, the image.
Where is it gone?
It's below.
It must be the ground matrix. I hope. It could make sense.
It does make sense. Yeah. I was wondering about the that incidence rate chart.
What is large? 400? 400? Oops.
That looks good.
Yeah, we should the lines better if we do this.
So where did you get that incidence rate from? From the Atlas map place?
The incident, the incidence rate. The incidence rate was which incidence rate? The
On the a little bit.
This there?
No, below. A little bit below. I think you got it from the Malaria Atlas project. You had a screen capture, right?
This there.
Yes.
This is from this map thing.
Maybe we can.
Malaria map site, yes.
Maybe you can open another on your Explorer or Safari, and let's look
check.
at.
Yes, 1 second.
Yeah, perfect. Well.
Whoa. No.
Well, there's one thing that we are not looking at, which is where do people live?
Yes.
Right. So Haiti.
Oh.
Because our model assumes everybody is living in the same spot.
Well, that's not ideal. That's less than ideal. Let's see. This is a night and it's probably turned. No, it's right.
Yeah.
So this bit is here, there.
That's Port-au-Prince. That's Dominican Republic. You notice that it's much more developed. You can actually see the line between one place and the other. So no.
Well, we have
There's a stagnant water. There's a lake in that red place on the where your icon is. There to the left of your there. If you do the geo image or
yes, I'll do that.
A normal map. I think there is like some sort of lake there. Is it geodynamic image or what's it? Let me see. range, quantity, 100 miles. Let me see if I can send you this.
Actually, what is this? This is another one.
You see that?
Look, this doesn't look so different from ours. This is multi-hazard, but look here. So this is red, this is red. This is red, this there's red. This is red, this is red, so this looks pretty much the same.
You see this? Look.
You see?
Yeah. No, what I was trying to figure out is if we look at the incidence rate
Yeah.
that we were looking at, there is a patch that it's red on the peninsula, right? That we do not see.
I'm not sure whether we look at the right bit. Because what does this say? This is the Malaria Atlas project, and they say this is global mapping, this is country level elimination mapping, and these two look very different. These patches, this is a very different type of structure. Here's red here, not so much here, there's a red spot there. So these two don't really coincide very well.
Okay.
But if I go to this other thing, which has more, this is...
But this is earthquakes, right?
Coast don't have the highest rate, but I think it's is it only earthquakes, or is it? Because it was on a website where it says malaria.
Oh, okay.
Let me see.
It is.
I think we need a good map of malaria in Haiti. Lots of details.
Let's look at your model again.
Mm-hmm. Yeah, we need probably this Oxford map thing there. whatever that is.
Yeah. Malaria. Yeah, if you open it up on your Safari, maybe we can see it there and explore the map in Haiti and take a look at incidence rates, tools and analysis. I don't want that.
Interactive map tool.
So you can select the country, Haiti.
Okay. No, not ideal, but not too bad either. Let me see. How do we do this?
There you go. Yeah.
And now this changes, I guess.
When was it there? Yeah, go to.
Oh, look, this looks like some of them.
Yeah, you have to go after the earthquake. When was the earthquake? Then, right? Because all the infrastructure went collapsed, and that's where you're gonna see the Haiti earthquake. 2010. So after 2010, you'll see the 2011.
Yeah, the pattern has changed, but after 2011 it's much worse because there are the two dots.
Yeah.
So that looks much more
like
this.
Yes.
But at other times, if you go to times before that, I guess it looks more like probably these.
Okay, so layer, you can use the prevalence rate, malaria risk, endemicity. There are many levels.
Yes.
Okay, so which vector occurrence, relative abundance, dominant vectors.
Oh. That's Africa, oh dear.
Why there?
This is on.
Yeah.
It's actually on relatively high ground.
Mm-hmm. Well, there are other factors that we're not taking into consideration.
Mm-hmm. Oh. Mm. Lots of maps on cholera.
Cholera?
Yeah, 90. So wait.
Yeah, there are some. Yeah, our model is just looking at temperature, but we're not looking at population density and other things, right?
Rainfall, humidity, and so yes.
Mm-hmm.
Still haven't found a good map on this.
No, that's not me. That's me.
Mm-hmm.
What is a spleen? That's the different types of mosquitoes. And the elevation. So 500 meters is the magic number.
Mm-hmm. Because okay, this is just the elevation. So that pattern obviously is like what we want to look at. And the mosquitoes are exactly where it's low.
Yes.
All around here, this is what we get to. Kind of here.
Yes.
Got mosquitoes here. Got mosquitoes there. Lots and lots of them there.
Yeah. So that has to do. So the other aspect that we don't have, the model is good because you have the temperature, right? So that's what's based on the one that says
Yeah.
they were looking at. The only thing I can think of between the one on the right that you're showing and the one on the left is that it's the amount of water or stagnant water.
Yeah.
Because that's the other condition. You need the temperature and you need the water, and that's the piece that we're missing from the equation. And I think what was it EOS? Land viewer. Let me send you this link. Try this. I'm going to send you a hyperlink. There it goes. So what I just sent you is, you see there it says EOS land viewer.
I don't think I've got it yet, do I?
No, you got it. It's above your input area. So you have to.
This one.
You see it says EOS land viewer. No, below, a little bit below. Go down. What you have is that box is yours. So you see it says eos.com land viewer. Yeah.
Yep.
So with this, you can that will open your Safari, and what it will do is that you can search Haiti, right? And perfect. And then you can use the type of satellite you want to use. Sentinel. You can use the filters section on the top. What is this? Filters, passive sensors day.
Don't know where.
Up. Go up. Where it says scene search, right? You're searching for a scene to the right. Up.
Yeah.
Up. And go to, no, it says filters. It's a circle with filters. To the left. To the left of where you are. There. So there you can say, oh, okay, I want the Sentinel 2C, which is great, right? And no cloudiness. So you can put a low cloudiness, like 10% or 0%.
Oh, yes, okay.
So you turn off all the sensors, and okay, so that's good. And the Sentinel 2, it's the one with a lot of definition. Yeah, perfect. So, and you can state a specific date, right? There you go.
Date? Do we want something special?
No, not necessary. And what that will do is tell you what images are there that comply with that. Let's try one. Just I wanted to show you what this does. Maybe if not, we'll do Landsat or something else. Just pick one that has. Maybe it's always cloudy over there. Just pick one. Yeah, let's do that one. Okay. So, oh shoot, you can log in with your. Let me explain what this can do. So you can select an image from the satellite, and if you go to the then there's some different layers and filters. So you can say, okay, show me water, and it will create a false image map and show you where the water is. So
yes,
and we can use that thing superposed with the other, right? Taking the image, and then you have a combination of water, prevalence of water plus the height that it's available. That could be an option.
Yeah. Let me just see.
Let me see if I can.
Do you want me to give you the screen back? Then you can.
No. I'll see if I can do something on this side. They don't have much images around here. Okay. Was water, agriculture, full scope, land, water.
Oh, look at this. This is, oh, that's nice, I think. Let me see. What do you think about, where's my chat window there? So this thing there,
Mm-hmm.
I want to execute it again. Gives me that image. Oh, come on. Well, you will have to write yourself.
Yes.
But in this one, it's easy to detect. I think that should be easy to detect the water because it's just black.
So, Marco, what did you think about the experience?
I think we should get a bit quicker. But when we made a model, we can look at images. I mean, I think we make progress.
Good. I think I recorded this. I'm gonna stop it from transmitting.
Mm-hmm.
Stop streaming.